Hello everyone, I am Dr. V. Himamaheswara, Assistant Professor of Physics, Department of Freshman Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today we are going to discuss X-ray spectrum, which is very much useful to evaluate the structure of atom. So in this lecture, we are going to discuss electron shells, characteristic X-ray spectrum, origin of X-ray spectrum, Moseley's law, importance of Moseley's law, and then references. Electron shells. So both discussed the structure of atom, and it is very much successful to discuss about the hydrogen atom. And later Bohr and Stoner extended the simple model of hydrogen atom to other elements also. So each atom is composed of positively nucleus at the center of atom, and around the nucleus there are different number of electrons revolving around the nucleus based on the atomic number Z. So the orbits to which electrons are confined are the orbits characterized by different values of the quantum number n. In general, if the atomic number is Z, so that number of protons are inside the nucleus here, and maybe there could be some number around the same number of electrons in the nucleus. Along with that, there are same number of electrons in the different orbits around the nucleus. There could be several orbits around the nucleus. So all the electrons are arranged in the different orbits like this. Maybe these orbits can be indicated as shells such as K, L, M, N. For example, here this is the K and this is the shell L, M, and N. Like this, we can give names as K shell, L shell, M shell, and N shell, etc. So here the principal quantum number for K shell is n equal to 1. Here it is n equal to 2, n equal to 3, like that, n equal to 4, etc. And again, the number of electrons according to these two scientists, Bohr and Stoner, the configuration of electrons in these orbits should be followed by, in the K shell, there should be only 2 electrons. So the filling of electrons should be followed by this value 2n square. 2n square. That means for n equal to 1, the number of electrons that could be filled in the K shell will be 2 only. And again, for L shell, the total maximum number of electrons is 8. So here 18. So all the numbers are given here. That means the capacity of any orbit are like this. For K shell, quantum number is 1, L shell 2, M 3, N 4, O 5. The number of electrons that could be filled 8 to 8, 18, 32, 50, like this. So the filling of these electrons in different orbits could be explained by the X-ray radiation emitted by elements. This gave very strong support for the hypothesis of these Bohr and Stoner. Okay, so whenever X-ray radiation is observed for different elements, emitted by different elements, we can see there are some fixed lines, the characteristic of X-ray spectrum. So the spectrum is similar for all elements, whatever the element, whatever the atomic number, the line spectrum. This could be also called as line spectrum. So the important observation from this line spectrum are that the X-ray line spectra of all elements are strikingly similar. So the line spectrum given off by an element remains the same irrespective of the compounds that the elements form. So whatever the element we take, but whenever X-ray spectrum, emission spectrum is observed for that particular element, we are getting the similar type of spectrum like this. This is the spectrum observed for molybdenum. So there are two lines, K alpha line and K beta line. So this same spectrum is observed for other elements also. But the major observation is that as one proceeds from the elements of low atomic weight to elements of higher atomic weight, the line spectrum shifts progressively towards shorter wavelengths. The wavelengths of these lines are decreasing as we are going from lower atomic weight elements to the higher atomic weight elements. That means for molybdenum, this is the spectrum for molybdenum. If we take atomic atoms of higher atomic number, the wavelengths, that means these lines are shifting towards lower wavelengths progressively. So as the atomic number is increasing slowly, these lines are shifting slowly towards the lower wavelength. But there is no any other change. These two lines are there presenting there, and the intensity is also almost the same, and the characteristic, this curve, this shape is also similar. The entire spectrum is similar, but the change is the wavelengths are changing. The wavelengths of the lines, these lines, the peaks are changing progressively. That means as the atomic number is increasing, these are decreasing, wavelengths are decreasing. So here, according to Bohr model, electrons in atom are organized into KLM shells, and an atom radiates energy when electron jumps from one allowed orbit to another allowed orbit. Okay, so whenever electron is jumping from higher orbit, outer orbit to the lower orbit, energy is released. So that released energy is also equal to the energy difference between the two energy levels, according to Bohr's theory. And again, normal electron transition cannot take place from the outermost orbit to the innermost orbits because the inner orbits are occupied. Generally, inner orbits are completely filled. There is no vacancy in general. So these transition, electron transition can happen from lower orbit to higher orbit, but higher orbit to, that means outermost orbit to the lower orbits is very difficult. However, when high energy electron knocks off an inner core electron belonging to K element shells, an electron from an outer orbit jumps to fill up the vacated inner orbit. So whenever high energy electron, maybe there is another electron coming from outside orbit, it can knock out the electron in the innermost orbit. So there could be a chance of an appearance of vacant place. So this vacant place can be occupied by electron which is coming from the outermost orbit. So whenever the electron jumps from outermost orbit to the innermost orbit, a huge amount of energy is released because there is a huge difference between the energy levels. So like that, for example, the binding energy of electron, that is nothing but binding energy. So the binding energy of electron in K shell of sodium atom is 1041 electron volt. So for K shell means this is the K shell. So the binding energy of electron, that means if you want to remove the electron from this shell, K shell, this much amount of energy is required. So that is the binding energy of K shell for particularly sodium atom. So the binding energy of a 2s electron in N shell is 63 electron volts. So L shell, K L M K L L shell. So for L shell, here electron in this L shell is 63 electron volt. So when the 2s electron jumps into 1s level from here to L shell to K shell, an X-ray photon of energy 978 electron volt is emitted. That means the difference between the two energy levels. Okay, so it is released in the form of X-ray photon, a huge amount of energy. So origin of characteristic X-ray spectrum. So whenever we observe the characteristics of X-ray spectrum emitted by different elements, we can see many important points. Those are it consists of series of discrete lines like K alpha. Here when the electron is jumping from L to K shell, that is called K alpha line. Here L to K shell, and M to K shell, that is K beta, and N to K shell, this is the N shell. So N to K shell, K gamma, then that is the K gamma. So similarly, we can form series. There are different lines, several lines, K alpha line, K beta, K gamma. So these lines are called a series, K series. And again, similarly, when electrons are jumping from higher orbits like M, N, O to the lower shell L, so there are also lines, X-ray lines, so that are called L alpha, L beta, L gamma, and this series, entire series is called L series. So there is also M series. And again, the K series form the most energetic. K series is the most energetic series of, and it is called hard X-rays. The series of K is forming hard X-rays, and the series like L, M, and those are called soft X-rays. Okay, so the summary of these observations are like line spectrum is produced when electrons are dislodging from innermost orbits of the atoms of the target material, followed by electron jumps from the outer orbits. It consists of discrete spectral lines which constitutes K, L, M, and N series. K series consists of those lines for which electron jumps end at the K level. Similarly, M series ends at M level, and N series ends at N level. K series lines are the most energetic and they constitute the hard X-rays, whereas L, M series form the soft X-rays. There is a regular shift towards, we already discussed this, there is a regular shift towards shorter wavelengths in the K spectrum as the atomic number of the target is increased. Okay, the relation found by Mosley between the wavelength of the emitted X-ray photon and the atomic number of target material is given by lambda 2 by lambda 1, and it also can be related with the frequency of the emitted radiation of the X-ray photon as it is inversely proportional. Lambda 2 by lambda 1 is equal to nu 1 by nu 2, and it is equal to Z1 minus 1 by 1 whole square by Z2 minus 1 whole square. So here it is Z1. Z1 is the atomic number of first target material, and Z2 is the atomic number of second target material. So as we are using two elements, Z1 and having atomic weight, atomic number Z1 and Z2, so these are the relation. This is the relation. That means wavelengths are inversely proportional to the atomic weights, atomic number. That means as the atomic number increases, wavelength of the lines decreases for particular line, like K alpha. For example, if we take K alpha line, the wavelength of K alpha line decreases as the atomic number of the target material increases. So mostly during the year 1913 to 1914, he made a systematic study on X-ray spectrum for different elements, and he found that different elements produce similar spectra consisting of KLM series. He measured the wavelengths of characteristics X-ray of large number of elements using Bragg's X-ray spectrometer. He found a striking similarity in the spectral lines of each series. The spectra emitted by each element was found to be exactly similar to that of the other, the only difference being that the lines had different wavelengths. The frequency of the particular line in a series varied regularly from one element to the next one in the periodic table. So it is also very important observation. So this is the same formula, uh, same relation identified by the Mosley. So whenever a graph is drawn between the atomic number of the target material to the frequency, like square root of mu by a, we are getting a straight line, whether it is k alpha, k beta, k gamma series. So we are getting straight lines like this. So with increasing atomic number, this also increases, this value, square root of v by a value also increases gradually, and it is the same straight line for all the elements. And we can derive the Moseley's law from Bohr's theory also. So according to Bohr's theory, the energy of uh, electron in different orbits is depends on the principal quantum number n, and it is also given like this: energy of an electron in the orbit, nth orbit. So it also depends on the charge of the nucleus. So if Z is the atomic number, then total charge Zt, and E is the charge of outer electron, revolving electron. So this is the energy of, if it is the nucleus. So if there is an electron in the nth orbit, so the energy of the energy of this electron in the nth orbit can be given by this formula. So if n1 is the quantum number, one quantum number of one particular orbit, for example, maybe this is n1 and n2, and then the energy is given like this: minus mz square e square 32 pi square by 32 pi square epsilon naught square h cut square into 1 by n1 square, and n2 is the electron in the n2 is the orbit of second electron. So then the energy is given like this. So energy difference between these two electrons, or if the electron from n to orbit is jumping from to the orbit n1, then the energy released by this X-ray photon can be calculated by the taking difference between the two energy values. That means En2 minus En1. And again here we are changing one more thing, that these are the values, energy values of that particular electron having in that particular orbit. But whenever the electron, there could be an inclusion due to the screening effect. Due to screening effect, so the electron experiences different attraction due to the presence of electrons in between these orbits. So we should include that value as a sigma screening coefficient. So for first n1 orbit, we are considering sigma 1, and for n2 orbit we are considering screening effect, screening coefficient around sigma 2. So we can calculate the energy of the X-ray emitted by the photon by taking the difference En2 minus En1. So we can take like this, and let us suppose these screening coefficients for the two orbits may be almost equal, and let it be sigma. So then we can simplify this equation to this one. This equation delta E equal to m e power 4 by 32 pi square epsilon naught square h cut square z minus sigma whole square into 1 minus n1 square minus 1 by n2 square. And again, here m is the mass of the electron, E is the charge of electron, epsilon h cut, all these are constant, and z is also constant, sigma is also constant. No, z can change. So we can take these values as constant, as here. If you want to frequency also, we can change it to frequency terms. So delta E by H, energy values can be converted to frequency terms here. So by H. So for the series, K series, due to transition from higher states to the n equal to 1 state, so N1 can be taken as 1 for K alpha K series, for K series particularly n equal to 1. So this is the equation we are getting, and as we are taking all these constraints along with 1 by 1 minus 1 by n1 square as a square. A square is the constant. Okay, so this is the Moseley's law. We already discussed about this law. So we can derive the Moseley's law from Bohr's theory. So the importance of Moseley's law in order to evaluate the atomic structure is identified, such as Moseley's work gave a precise method for determination of the atomic numbers of the elements. So basing on his work, Moseley concluded that determining factor in the arrangement of elements in the periodic table must be atomic number and not the atomic weights. In the earlier times, atomic weights are given preference in order to arrange the elements in the periodic table. So later, whenever Moseley work precisely identified, so the atomic number is given preference in order to arrange the atomic elements in the periodic table. Okay, so in general, if you are following the arrangement of atoms in the order of atomic weights, the cobalt, the element cobalt having atomic weight 58.94 should come after element nickel. Element nickel. So cobalt is having no 58.94. So it must come after the element nickel. But here cobalt atomic number is 27, nickel is having atomic number 28. So in the updated periodic table, cobalt, first we will see cobalt and then nickel following the atomic numbers. And similarly tellurium, in the case of tellurium and iodine, these atomic numbers are 52 and 53 respectively. But by observing the atomic weights, tellurium is having 127.61 units and iodine 126.92 units. So that means, according to atomic weight, iodine must come earlier than the tellurium. But by following atomic number, tellurium will be in the uh, first position before iodine. So in the case of argon and potassium, it is also same case. So according to Mendeleev observation, these are all the elements which should be in the reverse order according to Mendeleev. So this discrepancy is removed by the Moseley's observation. Thus, Moseley had shown that atomic number is much more important than the atomic weight in determining the properties of elements. And Moseley pointed out that gaps in the rare earth elements, gaps in the groups of rare earth elements at values Z equal to 43, 61, 72, and 75. These elements, technetium, promethium, hafnium, and rhodium, are discovered later, which should be present in the periodic table. These are the gaps identified by scientist Moseley. So this is the table we can see, like here, cobalt in the case of cobalt and nickel, and again, as we said earlier, here tellurium, iodine, and also gaps. These are the gaps observed in the Z equal 43, 61. These elements are not there in the periodic table earlier. So those gaps are identified by Moseley. Okay. So there is a proficient identification of atomic structure by Moseley's laws, which are using X-ray spectrum of elements. So with this, thank you for this your patience. Thank you all. These are the references. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.